This is problem 71, and we're going to solve it. First, we're going to take a look at what we are given. We're given a cube. We have a normal vector to one of the faces of the cube, and a green deformation tensor defined as gamma times identity minus the tensor product of that unit vector. What we are going to do is to choose a coordinate system that makes it easy to solve. Nothing easier than putting one of the coordinates in the direction of the normal tensor, the normal vector, sorry. So the components are as follow: 1, 0, 0. If we make the tensor product of that normal tensor, it's going to be 1, 0, 0, 0, 0, 0, 0, 0, 0. Now, if we apply that to the definition of the green deformation tensor, we end up with this, which C is going to be gamma minus 1, 0, 0, 0, gamma 0, 0, 0, gamma. Now we're going to get the eigenvalues. To get the eigenvalues, we're going to set the determinant of C minus eigenvalue times identity equal to 0. The tensor, after operating this, the tensor we are left with is gamma minus 1 minus mu, 0, 0, 0, gamma minus mu, 0, 0, 0, gamma minus mu. If we take the determinant of this equal to 0, we're going to have three solutions. One of them is repeated. The first one is gamma minus 1, the other two are gamma. Having two repeated solutions, that means that two of the eigenvectors doesn't have to be orthogonal, and they are going to define a plane. To find the eigenvectors, what we do, we take C minus mu times identity times the eigenvector equal to 0. For the eigenvalue equal to gamma minus 1, we are left with this tensor 0, 0, 0, 0, 1, 0, 0, 0, 1, and the components of the eigenvector that are unknown. So what we have is a system of equations, three unknowns. We solve it, and we have 1, 0, 0. This is 1 because it has to be a unit vector. And if we take a look at it, this eigenvector is equal to this normal vector. So it's a unit vector normal to the face of the cube. For the eigenvalue equals to gamma, we have this tensor, minus 1, 0, 0, 0, 0, 0, 0, 0, 0. The three components of the eigenvector that are unknowns, three equations, three unknowns. We solve them, and we are left with this 0, any number, any number. The thing is, this means that any vector containing the plane in the plane defined by the face of the cube is an eigenvector. So once we have the eigenvalues, calculating the principal stretches is really easy. The square root of the eigenvalues for the green deformation tensor are equal to the principal stretches. So the principal stretches are square root of gamma minus 1, square root of gamma, and square root of gamma. Now, we have to compute the stretch of the line AB. Given our coordinate system, a vector in the direction, a unit vector in the direction of AB, it's going to be 1 over square root of 2, 0, 1 over square root of 2. We know that the square of stretch is going to be equal the dot product of this tensor, of this vector, times the green deformation tensor operating on the same vector. So we have here the operation, and we are left with gamma minus 1/2. This is equal to the square of the stretch. So the stretch is the square root of gamma minus 1/2. To compute the Lagrangian strain, we're going to use the relation that we already know. The Lagrangian strain is equal to 1/2 of the square of the stretch minus 1. We have everything we need, so the Lagrangian strain is 1/4 of 2 gamma minus 3. So now the last two pieces of the problem is, when is the deformation feasible? Well, for the deformation to be feasible, all principal stretches must be greater than 0. We have two values for the principal stretches. They have to be greater than 0. This is more limiting than this one. Therefore, gamma must be greater than 1 for the deformation to be feasible. Now, we are told that there is no volume change when the determinant of C is equal to 1. We just take the determinant of C, which is this one, we equal it to 1. If we get the solution for this equation, we get that gamma is approximately equal to 1.466.